Hello everyone, my name is Mohamed Maouch from India, Lille, France, and I'm here to present our Interspeech paper titled Comparative Study of Speech Anonymization Metrics. In this presentation, we're going to compare three anonymization metrics using both simulation and evaluation on real speech data. Let's start with some context. So there is a wide number of smartphones available to users. Those smartphones have applications that ask for permission to get access to some data on sensors from the device, and the microphone that gathers speech data is one of the most asked permission, with 23%. With this microphone, we can have useful services such as personal assistant, automatic translation, and even new accessibility methods for disabled people. Unfortunately, sensitive information can be inferred from speech, such as emotion, health, and even spoken content itself. This is why anonymization is an important subject, and we are studying it in this presentation. So, to give our setting, we consider that the speaker anonymizes its speeches and send it to a public repository that is going to be used for different tasks such as speech recognition, speech analysis, training of some machine learning method. But an attacker tries to find the identity of the speakers inside this public repository using the found data for whom he has the identity of the speaker in it. The goal of this presentation is to compare the method that evaluate the quality of the anonymization method. To do this, we are going to use the speaker verification framework. So errors in verification are going to be considered as good for anonymization in this case. In this setting, there are two data sets, the public one, anonymized, and the found data, which is where the speakers are known. The attacker constructs an engage function that outputs a score. Higher the score is, higher the chances that the two utterances compared are from the same speaker. And this pair is called mated. And there are also non-mated pairs in these trials. Now let's speak about the anonymization metrics we are going to compare in this presentation. Starting with the equal error rate. In this setting, we consider that a decision is made based on a threshold. So higher, if the score is higher, the pair is considered as made. As we can see in the figure on the right, we have two distributions of scores, the non-mated one and the mated one. Then, given a threshold, we have two error rates, the false alarm rate and the misses rate. The error rate is the particular error rate corresponding to the threshold T star for which the two types of error are equally likely. Let's move to the second metric, the log likelihood ratio cost function. To define this metric, we're going to use the cost of detection function that sums the two error rates using the cost of errors and also the priors of receiving a mated pair. The goal of this LLR cost function is to construct an application-independent evaluation of speaker detection, and it's going to use LLR to do this. It's going to integrate the cost inside the prior, this new prior P prime H, and set the other cost to 1. Then it's going to construct this new threshold, this is logit of P prime, in order to be able to evaluate all of the probability of errors depending on this prior. By integrating over all data, we are actually integrating over all prior and costs of misses and false alarm. This is why this become application independent, because we are considering all of the cases. As it can be seen in the figure on the right, we have different probability of errors of cost 1 depending on the logit prior data, and the LLR is actually the area under this curve. In addition to this, the CLLR has a closed form calculation as a function of a set of scores to evaluate an anonymization method. Let's move further for this same metric. So CLLR is unbounded. It measures both discrimination and the calibration of the scores. But we are more interested only in the discrimination. This is why we go to CLLR mean that is bounded between 0 and 1. And to get this measure, we are going to use calibration that is conducted by finding the monotonic rising wrapping function over the scores that minimizes the CLLR, so we get CLLR min, and that measures on discrimination. You can also see it on the right figure. Even further, the EER can be found in this figure, which is the top of the curve that constructs CLLR min. Let's move to the third metric, the linkability. So in this measure, we actually want to look at the difference between the two distributions of mated and non-mated, considering that if they are overlapping totally, it means that there is unlinkability. We cannot link it. So starting from this local linkability for a given score, they defined it by focusing on the mated scores and using the LR and the prior ratio to construct this DCs, which is equivalent to linkability for the mated case. To go to the global measure of linkability, we integrate over all mated scores. We can see it easily in the figure on the right because we have the two distribution of mated and unmated. Then the linkability will be high for the cases where the mated distribution is separated and non-overlapping with the non-mated distribution. Overall, this is what linkability does. It computes the overlap between the two distributions. Now let's start the comparison, starting with the discrete scores simulation. Here we're going to compare EER with the LLR min. To do this, we're going to use 8 trials pairs. We are going to assign scores for the integers between 1 and 8. Then we're going to assign different labels to the pairs between mated and unmated in order to have different cases. For the example chosen here, we have 3 cases. We see that CLR min gave different levels of privacy while ER gave a fixed value. This is to show the generality of CLR min compared to ER that focuses on one single threshold. Let's move to another experiment on simulated data. Here, in this case, we're going to compare CLR min with DCs using Gaussians. So we have 3 Gaussians with means 1, 2, and 3. And then we're going to assign to each Gaussian also a label mated or unmated. Then we're going to sample from those Gaussians to get the list of scores. With these different settings of label, we have different cases. So either the mated scores are higher or the non-mated scores are higher, and cases where the scores are in between each other. We generate various cases with different standard deviation in order to have a multitude of examples. Let's look at the result. So here in this figure, which we show CLLR min compared to the unlinkability. We can see that for the mated higher case, both the metrics have similar conclusions. So in this case, they are almost equivalent. For the case of mated lower, since LLR min is awaiting for scores that are, the higher they are, the more chance that the pair are mated, the metric totally saturates and says that there is full anonymity. While linkability actually looks at the overlap of the distribution and tells us that there are different levels of privacy to be found here. For the in-between case, since there is always a third of the distribution that is false, CLR min is bounded by 0.6, so it has a lower bound, meaning that it's starting with some kind of error that is cannot manage. Let's see an example to see how this can happen. This problem can arise. So here we have an example. We have 2 speakers, speaker A and B. We see that the utterances of speaker A are either put in one of the 2 clusters on the left or the right, while speaker B is always put on the middle cluster. If we use our own data, which is the center of each of the cluster, and we compute all of the scores, this is the score distribution that we get. We see that here, this is an in-between case, and the measure of CLR min will give some level of privacy that is significant, while linkability will tell that there is 0 privacy. In this case, you can clearly see that there is more to extract from this cluster rather than saying there is level of privacy, because they are clearly distinctive to each other. Let's move to the evaluation on real anonymized speech. So there are going to be 2 experiments. In the first one, we are going to use the LibriSpeech dataset with enrollment data and trial set of LibriSpeech. And we're going to use 4 voice conversion techniques from the state of the art, including the Voice Privacy Challenge 2020 baseline. To be able to have different cases to study the differences between the metrics, we're going to have different choices of how to conduct the anonymization. First of all, there are different strategies for target speaker selection in the voice conversion techniques. You can either give the same target for all the utterances, have one target per speaker, or have a random target for each individual utterance. You can also go further with attacker types. Here we're going to consider different attackers with different information about the anonymization method. And depending on the information the attacker has, is going to uh, anonymize its anonymous set accordingly, and also even train the X vector extractor and the PLDA model depending on this anonymized training data. In the informed case, the attacker knows the anonymization method and even the strategy and even the target selected by the anonymization method, which is quite strong and not really realistic, but this is to have examples of strong attackers. We also have the semi-informed case where the attackers does not know the exact target speakers but know all about the anonymization method, even the strategy. And finally, we have the ignorant, where only the attacker doesn't know about anonymization, he just considers it as clean data. We even have three linkage function, PLDA, cosine, and Euclidean. In total, we have 72 cases. Let's look at the results, where first of all, we compare CLR mean with EER, and we see that they give the same conclusion. We also draw for each individual case the difference between the mean of mated and non-mated scores. Let's see now the difference between CLR mean and 1 minus thesis. We can see that they agree and they give similar conclusions on all of the cases, but we can also see that all of the cases are either white or red, meaning that they all fall in the category where the mean of mated scores is higher than the mean of non-mated scores. Let's go further and search for other cases. We are going to use the VPC baseline with the work done on another paper of Interspeech where they studied different design choices for the X vector based anonymization method. So here we're going to have 4 data sets from Hebrew speech, so test, male and female, and dove, male and female. I'm going to have different proximities, which is the way to select the region we're going to construct the target X vector that is going to use for the anonymization. We have also policies for the gender selection. Is it same, random, or opposite? Different granularity levels of anonymization, and 2 different similarity measures, cosine or PLT. We also have in this case 3 attacker types. Here, semi-informed knows the anonymization method and uses the same strategy to anonymize its training data. Semi-ignorant doesn't retrain its models but anonymizes the own data, and the ignorant case doesn't care about the anonymization. Let's look at the result when we compare CLR mean with the uniqueability. Here we can see that they agree in many cases, but if we zoom at this particular rectangle area, you can see that some cases where the mean of non-mated scores is higher, and we see that they are the ones that are even further from the diagonal, meaning that the 2 measures agree less and less. So here we even have 70 compared to 95, which is quite a difference. Let's move to the conclusion. So here in this paper, we compare 3 anonymization metrics, 2 that are based on threshold decision, and 1 that tries to model every possible distinction between mated and non-mated score distribution. We used simulation to compare the fundamental differences between these metrics, and we conducted experiments on real data with different set of the anonymization techniques to show few cases where CLR mean and thesis behave differently. Overall, the uniqueability measure had more cases that was managed correctly by the measure compared to CLR mean. We are actually exploring where the benefits of this linkability measure come from. Our preliminary insight is that two methods have different ways of estimating the LLRs, and maybe the method used by linkability is better, even if the LR mean has good theoretical foundations. Thank you all for viewing this presentation. Hope you enjoyed it. Here's my contact, and if you have any question, feel free to ask. Thank you.